About 3 years ago now, I made a video about the basic concepts of quantum field theory and how it compares to a classical field theory, and for absolutely no reason at all, I've been wanting to make a follow-up video on the subject. In all seriousness though, after going through a lot of the comments and having some discussions with viewers, it seemed to me that there were some points that I wanted to clarify, as well as some misconceptions that I really wanted to clear up about the subject. It also gave me an excuse to play around and create some new animations, but I'll get to that later. Now, before I get into the actual video, I wanted to say that I tried to be as thorough as possible with this video. So in the link in the description, you'll find a document going into the excruciating details of the calculations that I did to get the results that I'll show you in this video, as well as some of the code that I wrote to create the animations. I will say, though, that the document gets pretty technical, and it's not necessarily for the faint of heart. Now, I put a lot of work into this video, and I had a ton of fun making it, so if you enjoy the video, or you feel like you learned something, then feel free to leave a like or a comment, or even share with someone else who you think might like the video. Any of it really helps the channel. Also, I know I'm not necessarily the best coder in the world, so if you're an expert in that sort of thing, I'm always trying to learn more, so if you have any tips, then feel free to let me know. Anyway, with that said, let's get on to the actual video. Now, first and foremost, I want to address a point that I don't think I emphasized enough in the previous video, namely how we get particles out of a quantum field theory. To start, I'm going to quickly recap the discussion of that video, but if you want more details, I would recommend just watching the original video if you haven't already. So in classical mechanics, we can get the simplest possible field theory, namely the wave equation, by taking regular, identical, simple harmonic oscillators, like masses connected by springs, and connecting more and more of them together, putting them closer together as we do. Eventually, when we take the limit where we have an infinite number of oscillators infinitesimally close to each other, we end up with a field. Now, the story is actually nearly identical in a quantum theory. We can form the simplest quantum field theory by just stringing together more and more identical quantum harmonic oscillators, which are allowed to interact with each other. The key difference between the classical and quantum cases is instead in the fundamental behavior of these component harmonic oscillators. It turns out that quantum harmonic oscillators have a very different qualitative behavior than their classical counterparts. In this particular case, it's better to think of an individual quantum harmonic oscillator as a localized site into which we can place or take away energy. However, these sites don't take in or give up any amount of energy, but only do so in integer multiples of exact values determined by the properties of the oscillator. Once we start stringing together more of these quantum harmonic oscillators, we allow them to pass these units of energy between each other, and they actually begin to accept different values of energy, but still only in discrete values. The number of different values of energy that the oscillators accept is equal to the total number of oscillators we've connected. For the more technical folks watching, the distinct energy values accepted by the quantum system directly correspond to the normal mode frequencies in the classical case. However, in the case that we're considering now, which eventually becomes the non-interacting quantum field theory, it's important to note that the discrete chunks of energy in the system can't be converted between values. So, for example, even if we have a system which accepts units of energy, say omega and 2 omega, a unit of energy 2 omega can't be converted into 2 units of energy omega. Again, more technically, this is because each state with a discrete number of energy units in it is an energy eigenstate, so won't change when evolved in time. I want to emphasize that this story can change when we move to an interacting field theory, but for right now we're only considering non-interacting theories. Eventually, when we take the n to infinity limit, the system as a whole will accept units of energy with an infinite number of different values, but any one energy value can still only have a discrete number of units in it. So, if we place one unit of energy into the system, there will only ever be a single unit of energy in the system. This is the particle-like nature of a quantum field theory. One difficulty with this story comes up when we're considering the uncertainty principle. Say that we want to place a single unit of energy in our field at a particular point. Well, the uncertainty principle tells us that if we want to know exactly where that unit of energy is, we can't know the momentum, and therefore the energy at all. So we don't know which momentum state we actually put that unit of energy into. The resulting state is therefore an equally weighted sum of all possible single unit momentum states, and we now have no idea exactly where the particle is going to end up. So, if we want to try to pull that single unit of energy out of the system sometime later in a different place, we won't be able to get a definite prediction of where it will be. Instead, we have to describe the system with the probability to find the unit of energy at any one point. However, since there's still only one unit of energy in the system, we will still only detect it at a single point, even if the probability distribution is spread out over space. So if we go back to the animation in the previous video, and we look at the two red dots zooming around the circle, these aren't particles per se, but instead the probability distribution of finding the single particle that we put into the system at some point after a given time. The fact that there are 2 points is exactly attributed to this uncertainty principle. The theory is massless, so any excitations are restricted to travel exactly at the speed of light, or sound in this particular example. But there's complete uncertainty in the direction of travel since we put the particle in initially at a single point. This results in a probability density of 2 points traveling in opposite directions. Furthermore, the infinite uncertainty in momentum means that if we do detect a particle, we can't say ahead of time what energy that particle will have. This whole story becomes a bit more clear when we consider the same massless field theory, but upgraded to 2 dimensions. We'll look at both the classical and quantum cases where we have a detector consisting of a thin ring. We'll then excite the field at the center of this ring. In the classical case, we'll just disturb the field, and in the quantum case, we'll add a single unit of an unknown energy, and wait for the corresponding excitation to propagate to the detector. We'll show the amplitude of the wave in the classical case, and the probability density in the quantum case. In particular, we can note that when simply propagating, the 2 theories look remarkably similar. The probability density of the particle in the quantum theory looks pretty much identical to the wave amplitude in the classical theory. However, this changes once the field excitations hit the detector. In the classical case, the wave imparts some energy at every point on the detector, spreading it out over the full thing. In the quantum case, since we can only have discrete units of energy, and these units can't be shared among sites, when the detector sees the field excitation, it sees it at a single site, of course up to some uncertainty in the measurement. So in the quantum field theory, we placed a single unit of energy at a single point, and we detected that same unit of energy at another single point. This is exactly what we would expect from a particle. We just won't be able to predict ahead of time what exactly the energy of the particle is, or where it will end up in the detector. Now, another thing that I noticed a lot in the comments of the last video is that people really expected this probability distribution to smear out over space. Now, I'm not exactly sure about this, but I think that this intuition actually comes from the non-relativistic Schroedinger equation, where even if we start with a relatively localized probability distribution, it does indeed smear out as the system evolves. Now, one thing that we really have to remember is that the quantum field theory obeys special relativity, whereas the non-relativistic Schrödinger equation doesn't. In particular, one of the consequences of special relativity is that massless particles, like the one we're considering here, have to travel at the speed of light. This means that you can't end up with a smearing or spreading effect like you see in the non-relativistic Schrödinger equation. One way to really think about this is that every piece of the probability distribution has to travel at the same speed, though its direction can vary based off of its momentum. Of course, this story changes for the case of a massive particle, which in the case of the relativistic theory is restricted to travel slower than the speed of light, but has no such restriction in the non-relativistic theory. To visualize this, let's go ahead and continue looking at one-dimensional theories, but this time we won't restrict the particle to a circle, and we'll let it travel across an infinite single dimension. Unlike the animation in the last video, where we started with the particle at a single point with infinite uncertainty and momentum, we'll now start the particle with some momentum, which we'll only know up to some finite uncertainty. By the uncertainty principle, this will then induce some finite uncertainty in the initial position as well, so the probability distribution will start with some initial spread in both the position and momentum. In the Schrödinger case, the uncertainty in momentum essentially means that different parts of the probability distribution will be trying to move at different velocities, therefore pulling it apart and smearing it out. We'll start by looking at what's perhaps the simplest case, where the mass of the particle is much larger than both its initial expected momentum as well as the spread in momentum, which we should expect to reduce to the non-relativistic result. Sure enough, when we overlay the two, the evolution is pretty much exactly the same. The probability density moves much slower than the speed of light, and we see that the characteristic smearing we expect from the Schrödinger equation also appears in the quantum field theory. So indeed we see that the fully relativistic quantum field theory reproduces exactly the results we get from the non-relativistic theory when the particle is restricted to traveling much slower than the speed of light. Next, we'll consider the case where the particle's expected momentum is equal to its mass. If we work it out, this should correspond to the particle traveling about 70% the speed of light. Here, we see a big difference between the two theories. Just like before, the Schrödinger solution smears out as expected, but the behavior of the QFT result is much different. It does indeed smear out, but the smearing seems to sort of bunch up on the leading edge of the distribution. The reason for this is simply due to the fact that the particle can't travel faster than the speed of light. This means that the higher momentum contributions from the uncertainty principle just correspond to pieces where the particle is traveling closer and closer to the speed of light. So this bunching effect should be expected. This is all of the high momentum pieces collecting traveling near the speed of light. Contrast this with the Schrödinger case, where the amount of smearing is essentially the same as before, causing the leading edge of the distribution to zoom off ahead of the speed of light. Finally, if we look at the case where the expected momentum of the particle is much larger than its mass, we hardly see any smearing in the QFT result, which is restricted to move very close to the speed of light due to its high momentum. Like before, this means that the momenta contributing the most to the process within the uncertainty range will also result in the particle traveling near the speed of light, meaning that all parts of the distribution pretty much move at the same velocity. Since the Schrödinger solution has no velocity restriction, the high momentum results in a very high velocity, and the distribution flies off ahead of the speed of light, almost before you can make it out. Remember that in each of these cases we just considered, we put a single particle in and measured a single particle sometime later, and the distribution shown is describing the probability of measuring the particle at any one point at any one location. This interpretation is the same regardless of whether we're looking at the QFT or the non-relativistic Schrödinger equation. The difference is simply due to the fact that the QFT naturally respects the symmetries of special relativity, while the solutions to the Schrödinger equation do not, as is clearly seen when comparing the motion of the distributions to the speed of light. Now, of course, it's very interesting to see this natural Lorentz invariance of a quantum field theory versus the non-relativistic Schrödinger equation. But everything we've considered up to this point has been a non-interacting quantum field theory. Of course, these aren't really physical, since we see particles interacting with each other in nature. So I think many viewers of the last video really wanted to see some sort of visualization involving interactions, something like quantum electrodynamics. So I wanted to make a similar animation to the one you just saw, but with a simple interacting theory. Now, the goal here will be to introduce two scalar fields, like the ones that we've just been calculating with so far, which we'll call phi and theta, whose associated particles have two different masses, which will give the names of m phi and m theta, respectively. We'll then add in the simplest, most symmetric interaction that we can have between the phi and theta fields and try to see how that affects the dynamics of the theory. But before I get into that, I want to preface this whole discussion with the well-known fact that interacting quantum field theories tend to be extremely difficult. But why are these theories so much more difficult than their non-interacting counterparts? Well, the short answer is that the whole notion of field theories, quantum or classical, as a collection of simple harmonic oscillators, breaks down when we start to introduce interactions. In the quantum case, this means that for most interacting theories, it's not known what the fundamental constituents, the particles, of the theories really are, even if the field content is known. Now this may seem very odd, but it can be seen in a somewhat familiar case, namely that of quantum chromodynamics. In this case, the fields that make up the theory are the quarks and the gluons, but these aren't the particles that we observe in experiments. Instead, we only see hadrons, such as pions or protons or neutrons, at least at low energies. In a more technical sense, this is due to the fact that the interactions sufficiently change the dynamics of the theory to hugely alter the eigenstates of the QCD Hamiltonian, from just the free particle quark and gluon states with interactions turned off. In fact, it's actually not known in general how to analytically compute the particle spectrum of an interacting QFT, so we have to resort to some approximation techniques such as perturbation theory, where one assumes that the exact results can be expanded in a series in a small parameter of the theory, where each individual term is calculable, or lattice computations, where space-time is split up into discrete points, and observables can be numerically calculated using a variety of computational methods. However, even these approximations are no walk in the park. Perturbative calculations typically involve challenging integrals with very tricky analytical behavior, on top of the appearance of annoying divergences that have to be treated very carefully. And lattice calculations require a huge amount of computing power and time to achieve reasonably small errors in the numerical calculation. To put all of this into perspective, here is the setup and calculation for the animations that I just showed of the non-interacting case, starting from basic quantum mechanics and classical field theory, where this is the setup and calculation needed for the interacting theory. And keep in mind that this is one of the simplest interacting theories there is, and only the leading order calculation in perturbation theory. With all this said, what does our animation actually look like in this simple interacting theory? Now this was something I was really excited to put together, but unfortunately the final result ended up being a momentum space integral that has some very tricky analytical behavior, and I wasn't able to find a good way to evaluate it either analytically or numerically to get a sensible animation. Now, of course, this isn't to say that it can't be done, so if you want to give it a try yourself, please feel free. All of the work that I did to find the result is in the PDF in the link below. And actually, I'm really curious to see what people can come up with, so feel free to leave a comment or send me a message if you're able to come up with a solution, and I'll happily feature it in a future video. Now, while this is of course a bit disappointing to not have this particular visualization, it isn't really the end of the world. This sort of calculation, namely the calculation of correlation functions between separated spacetime points, is notoriously challenging and is typically what one studies in formal quantum field theory. However, in particle physics contexts, this isn't what we really want to calculate. Instead, we're more concerned with what happens in particle experiments, where we prepare collections of particles and shoot them at each other to produce a different final state that then flies into our detector. In short, the setup we actually want to look at in particle physics is an initial, non-interacting state, with particles separated very far from each other, which then interact for a very short amount of time to create a final state which is again largely separated and non-interacting. Now this picture can actually be translated into mathematics, which corresponds to calculating what are known as S-matrix elements. These S-matrix elements exactly describe the transition from non-interacting initial to final states due to short-time interactions, and amazingly turn out to be substantially simpler to calculate, particularly in perturbation theory, though that doesn't mean that they're easy by any stretch. The difference is that the physical observables that we extract from the theory are no longer probabilities of creating and annihilating particles at exact points, but instead the expected rates at which interactions occur. This means that if we build an experiment where we know the type and number of initial state particles, we can predict the number and momentum distributions of certain types of final state particles. So for example, if we take our simple model from before with two interacting scalar particles, we can build a theoretical collider which smashes two beams of phi particles together with some given experimental parameters. We can then make predictions for the rates to produce the four most likely final states, those being the 2 theta state, the 2 phi state, the 4 theta state, and the 2 phi 2 theta state. And the results look like this. To make this plot, the intersection angle of the two beams, the width of the beams at intersection, and the number density of the beams and respective masses of the two particles are held fixed, while the energy of the phi particles in the initial beams is varied, plotted on the horizontal axis. The vertical axis plots the rate of interaction for a given final state. We can already see that even in one of the simplest models that we can cook up, some very interesting features arise, like energy thresholds for particle production, which just tell us that an interaction can't take place if we don't have enough energy to produce the final state particles, at least at rest, and these peaks here, known as resonances, where intermediate states are produced on shell, or at least nearly so, only to then rescatter into the final state of interest. Now, I won't go too in-depth on these features since I want to make a separate video dedicated to this discussion, but suffice it to say that even these quote-unquote easiest interacting models in the framework of quantum field theory feature quite a lot of complexity. Now, unfortunately, due to the nature of computations of S-matrix elements, where we assume that particles begin and end very far from the point of interaction, we can't actually create animations like this one for our interacting theory based off of such calculations. We can, however, get a different visualization of what these S-matrix elements are really telling us by simulating what we would expect to see in an experiment with some chosen parameters. To do this, we'll create a detector which lives far from the interacting region of the two beams, which we can make small by tuning the relative angle and width of our two phi beams. We can't know what's going on between the interaction region and the detector, but since the detector lives far from the interactions, and the interactions remain weak, the rates at which we expect to observe certain particles is exactly given by the S-matrix elements. Then, we'll represent observed phi particles as red and observed thetas as blue, and show each particle hitting the detector as a line of varying opacity, indicating how much energy they're imparting on our detector in a given region. The lines will start off lighter and get darker due to the fact that particles are less likely to scatter in the detector when they have high momentum, but with each scatter, they transfer a bit of their momentum to the detector, making subsequent scatters more likely. This means that generically, the particles will deposit most of their energy at some depth in the detector. Now this isn't fully true, since there's some non-trivial mass dependence, and the exact details would depend on the makeup of the detector, but it suffices for our simple simulation. Now, putting all of this together, we end up with an animation like this. Now this simulation is accounting for the 4 different processes shown in the previous plot, and we can actually see the way that the interactions separate out based on how they share the initial state energy. The lighter, red phi particles penetrate deeper into the detector than the blue theta particles, when pair produced, since some of the spatial momentum of the initial state phi's has to be used to create the much more massive thetas. When more particles are produced in the final state, they have to share the energy amongst more particles, not only making it so that they don't go as deep into the detector, but also that these final states have more variation in terms of their detector signal, since they have different ways of distributing the energy between all of the particles. Since it's kind of hard to see while the animation is going, I've grabbed a couple of still frames, one showing a 2 theta 2 phi event, and one showing a 4 theta event. Now, I don't want to go too much more into detail about this particular animation in this video because, well, first of all, this video is already getting quite long, and also I want to talk about it in a future video. But as I mentioned previously, all of the code that I used to make this animation, as well as the explanation of it, are given in the GitHub link down below, so feel free to play with it yourself. Of course, what we talked about in this video doesn't even begin to scratch the surface of the study of quantum field theory as a whole, and I'll definitely be making more videos on related topics in the future. But in the meantime, I hope that you enjoyed this video and that it's given you a bit more insight into what quantum field theories are actually describing, as well as the fundamentals of the types of calculations we do in particle physics.